Hey everyone, welcome back to the channel. It's so great to have you here with me today. Before we dive into one of the most incredible ideas in all of physics, I just want to take a quick moment to say that I genuinely hope you are feeling happy, healthy, and safe. Wherever you are in the world, take care of yourself and those around you. Now, get ready to have your mind completely bent, because we're talking about how time itself is not what we think it is. We all have a feeling for what time is, right? It's that constant, steady tick-tock that moves us from the past, through the present, and into the future. It feels universal and absolute. A second for me feels like it should be exactly the same as a second for you, no matter where you are. But what if I told you that's completely wrong? What if I told you that time can actually slow down? And not in a metaphorical, time flies when you're having fun kind of way, but in a real, physical, measurable way. This mind-bending effect is called time dilation, and it happens because of gravity. The simple, unbelievable rule is this: time moves slower in a stronger gravitational field. The stronger the gravity, the more time slows down. This isn't science fiction. This is a fundamental feature of our universe, as described by Albert Einstein's theory of general relativity. To even begin to wrap our heads around this, we have to let go of the idea that space and time are separate things. We usually think of the universe as a three-dimensional stage, with length, width, and height, and that time is just a universal clock ticking in the background, independent of everything else. Einstein realized this was a mistake. He proposed that space and time are woven together into a single, four-dimensional fabric called space-time. Imagine a giant, stretchy rubber sheet. That sheet is space-time. Now, what happens when you place a heavy object on a stretchy rubber sheet? It creates a dip, a curvature. A bowling ball would make a deep dent. A marble would make a small one. This is exactly how gravity works. Objects with mass, like our Earth, the Sun, or you and I, warp and bend the space-time around them. The more mass an object has, the deeper the dent it makes in space-time. Now, here is the crucial part that leads to time dilation. This curvature of space-time doesn't just affect the paths of objects, it literally affects the flow of time itself. Think of the fabric of space-time as containing both the grid lines of space and the ticking of time. When that fabric is stretched and warped by a massive object, the ticking of time gets stretched out too. It has to take a longer, more dilated path through the curved geometry. So, if you are down deep in a gravitational well, like here on the surface of Earth, you are sitting in a place where space-time is more curved compared to someone floating out in deep space. From the perspective of that person in deep space, your clocks are ticking slower. Your time is literally moving more slowly than theirs. You wouldn't feel any different. To you, a second would still feel like a second. But if you could compare clocks, you would see a real, measurable difference. This has actually been proven, and we use this knowledge every single day. The Global Positioning System, or GPS, is a perfect example. We have a network of satellites orbiting high above the Earth. Because they are farther from Earth's center of mass, they are in a region of weaker gravity. This means time actually runs faster for the satellites up there than it does for our clocks down on the ground. But there's another effect from Einstein's special relativity. The motion of the satellites also makes their clocks run slower. However, for GPS, the gravity effect wins out. The net result is that the atomic clocks on the satellites gain about 45 millionths of a second per day compared to clocks on Earth. That might sound tiny, but if the GPS system didn't constantly correct for this time difference, the calculations for your location would be off by about 10 kilometers or 6 miles every single day. Your Maps app would be useless in a matter of minutes. So, engineers have to program Einstein's equations into the system to account for the fact that time runs at different rates in different places. The most extreme example of this is a black hole. A black hole is an object so incredibly massive and dense that it creates a bottomless pit in the fabric of space-time. Its gravity is so strong that not even light can escape it. The gravitational time dilation near a black hole is insane. Imagine a brave astronaut on a spaceship, somehow able to hover just outside the point of no return, the event horizon. She would be experiencing time normally from her perspective. But if we could watch her from a safe distance far away, we would see something utterly bizarre. Her movements would appear to be in extreme slow motion. Her heartbeat would take years. A single blink of her eye might take a decade. As she got closer and closer to the event horizon, from our view, her time would appear to slow down so much that it would almost completely stop. She would seem to freeze there forever at the edge. Of course, from her perspective, she would cross the event horizon and her time would continue normally, but that's a story for another day. This thought experiment shows just how powerful gravity's effect on time can be. This also means that you are technically aging at a slightly different rate depending on where you are. If you live in a penthouse apartment on the top floor of a skyscraper, you are very slightly farther from Earth's center of mass than someone living in a basement apartment. The gravity at your head is microscopically weaker than at your feet. This means time actually runs very, very slightly faster for your head than for your feet. And it runs faster for you in the penthouse than for your friend in the basement. The difference is unimaginably small. Over an entire human lifetime, the person on the top floor would age about a few millionths of a second more than the person in the basement. You could never perceive it, but with incredibly precise atomic clocks, scientists have measured this exact effect right here on Earth. It is real. So, what does this all mean? It means that the universe is far stranger and more wonderful than our everyday experience suggests. Time is not a universal metronome ticking away in the background for everyone. It is a flexible, malleable, and personal thing. Your rate of time depends on your address in the gravitational field of the universe. It's a profound shift in perspective. We are not just in space and time. We are part of a dynamic, interactive fabric of space-time, and our motion and position within that fabric directly shape our experience of reality itself. The next time you look at a clock, remember, it's not just measuring time, it's telling you the story of the gravitational landscape you are currently in. Thanks for watching, and as always, stay curious.